The second idea that I want to cover in this lecture is something called completeness and compactness. These are two different concepts, but they're intimately related, and understanding how they are related in the context of the real numbers is very important. It is perhaps one of the most important properties of the real numbers in terms of topology. So remember something that we mentioned in chapter 3 when we were constructing the real numbers, and it was written down, but it was left without proof because I decided to leave it for later when it becomes more relevant, even though I think we have used it at least a couple of times. And that is the fact that the real numbers are complete. Said in other ways, every non-empty bounded set or upper bounded set of reals has a supremum. A supremum is a lowest upper bound. Now, to explain what this means is essentially, this is not true for the rational numbers, right? So for the rational numbers, you may remember, and I will just write this and then delete it. You may remember that if we take, for example, the set of all rationals, such that when I square it, this is less than 2, this is a set that is bounded. It is bounded above, and it's also non-empty. But this one doesn't have a supremum, because whenever you try to approach and find the lowest upper bound, the lowest upper bound of this, the supremum, is of course the what we would call the square root of 2, which is no longer rational. So this property is very particular to the real numbers, and it tells you in a way that the real numbers don't have any holes in them, like the rationals do. And there's more than one way of understanding this. The rest of this chapter will be devoted to understanding what completeness means. But in doing so, we will develop techniques that relate to other concepts and other proof techniques. This like everything we do is just an excuse to learn new proving techniques and how to write arguments that become more and more complicated. Okay, so how would the proof go? And this proof does not explicitly reference anything that we did in the construction, but it is based on the construction that we did in chapter 3. Nevertheless, it makes more sense to look at this proof in detail now, since now is when we will relate this to other things. There's two equivalent ways of formulating what it means for the real numbers to be complete, by the way. One way is the way that it is written in this theorem. Another way is that you can define what it means for a sequence to have a limit, like we did above, actually, in the real numbers, right? And we also defined the concept of a Cauchy sequence. And we can do the same definition for the real numbers, not just rational numbers. So something that is very easy to prove is that if you have a sequence that converges, then this sequence has to be a Cauchy sequence, right? If it approaches a particular point, then in particular, these points need to approach each other. So it's a Cauchy sequence. What is not obvious at all is that the converse is also true. In other words, if you have a sequence that is Cauchy, it must converge. This is not hard at all to prove from the way that we constructed the real numbers, because the real numbers are exactly that. They are defined as all the possible limits of Cauchy sequence, even the ones that don't converge in the rational numbers. So you're adding every possible limit of rational numbers in a way, and that's how you get the real numbers. We will cover the more useful version of the theorem, which is what I'm about to write now. I'm about to write down now. But later we will see that these are all equivalent and in fact related to this other concept of compactness. Now, let me just add one more word as to why we would care about doing this. Completeness, the way I wrote it now, is a property of order, right? A supremum, lowest upper bound. This is all talk about this symbol, about the real numbers, right? It's a property of the order. If we're talking about Cauchy sequences, well, sequences are ordered or interact with each other with these two symbols, the operations. So that would be like an algebraic approach to completeness. The one we have now is like a set theoretic approach to completeness. If you want a topological approach to completeness, that's when compactness comes into play, because compactness doesn't talk about algebra or order. Compactness just talks about shape, right? So I know this might seem a little bit abstract. It will make sense once we see all these different approaches. But just so you know, just as a heads up, the point of the rest of the chapter, so this lecture and next week, is to understand completeness in these three contexts. Okay, so let's just write the proof. It's slightly technical, but it isn't really a difficult proof. What we're doing essentially is showing that if you can prove that every time you have a Cauchy sequence, it must have a limit, then this limit can be used to construct this supremum. So let's write this in whole details. So let's see. Let E be a subset of reals. We could do something similar. There's a way to define completeness for Rn. Of course, the supremum doesn't make sense anymore because Rn isn't ordered as a line, but Cauchy sequences and all of that still makes sense. So this is a very particular case of this theorem, right? But we will only really care about this for the real numbers. So let's consider the real numbers. Let's take a subset and let's say that it is non-empty. And we need an upper bound, right? Because the theorem states if it has an upper bound, then it has a least upper bound. So let's assume that there is an upper bound. And let me see, can we call it just let M be an upper bound? Any upper bound. Right. Now, something worth noting is, okay, so let me write this here. Using the Archimedean property, this has to come into play because otherwise all of these theorems are no longer equivalent if we don't have the Archimedean property. I think I added a comment about this either in the tutorial, in next week's tutorial, or maybe in the problem set, but this is definitely mentioned. The fact that the Archimedean property is you cannot really avoid it. Using the Archimedean property, assume the following. That we have, actually not assume, using the Archimedean property, we can conclude that we have M, let's say this is another real number that is not an upper bound, right? Not everything can be an upper bound because of the way this is set up, so that is not an upper bound. And how do we use the Archimedean property for the next bit? We're going to define, the Archimedean property talks about natural numbers, right? So define natural number such that B0 is an upper bound. So anything that's overtaking this upper bound. But if I subtract 1 from it, it is not. Right? So maybe I can leave this conclusion to you as an exercise. How did we conclude this? Because it is once again an application of the Archimedean principle, you have to put lowercase m and uppercase m in the right order to get this number B0. But if I may add a quick sketch as an explanation, and I did not just want to do that. If I may add a sketch as an explanation, you'll see that this is actually very intuitive, and maybe we're being a bit pedantic by citing the Archimedean property, but we're just being thorough. Okay. I think I may need to delete this because if it's going to take a minute to render that way. So what is happening is the following. We have some set of reals E, and it doesn't have to be connected, right? It can be something messy like this. We know that it is bounded by some number M. Since it's not empty and not every real number can be a bound, there must be something that is not a bound, so M, right? So all I'm saying is that if you keep looking in this direction, eventually you will find a natural number that is still a bound, B0, but it is the smallest such bounds, right? Actually, we don't need this right now. So you can use this property, Archimedean property, and then the least actually, sorry, there's a tiny mistake here. The least the what do you call this? The well-ordering principle, right? So you keep scanning right to left until you hit the set, and that happens at b0. So the next natural number is no longer an upper bound, right? So this is like the least upper bound, but it is a natural. It's an integer, so we can't quite yet conclude what we want because we want to find a least upper bound, but in terms of the real numbers. And this is definitely not that because if I zoom in, you can see there's a bunch of stuff here that's still in between, right? So that is not a supremum yet. Okay, let me adjust this. There you go. So let's just continue with the formal proof, and there will be time for questions in the end. I mean, I know this isn't live, but you get the drift. So now we have to repeat this process. So define recursively or by induction. I have said this before, but recursion is basically induction to construct things, and induction is to prove things, right? But they are the same uh, principle in a way. So I'm going to define Bn, and if B0 is already close enough, then we don't have to do anything. And if it isn't close, we can still wedge something in between. So let me tell you what I mean. You take the previous number that is already defined, because this is what we're assuming by induction, and we're going to subtract something very small. So let's say 1 over 2 to the n, something that becomes smaller and smaller, in case it is still an upper bound when we do this, right? If bn minus 1. So if after subtracting this, this is an upper bound, then we take that. And if it isn't, if it's no longer an upper bound, then we shouldn't change it, right? Then we should just get stuck in it until we can find a smaller number. So this is otherwise, right? So what we're doing is basically we have b0 up here, right? And we're going to take a step to the left, a very small step. So this is a step where we subtract 1/2. Okay, in this case, in the drawing, it's no longer an upper bound. I fell somewhere in between, not necessarily inside of E, right? It could be something that is not an element of E, like in this example. So this is not what we want. This was a bad step. So we have to go smaller. We continue doing this 1/2, one quarter. Wait, it's part of 2, right? Yes, 1/2, 1/4, 1/8, and so on, until we find a step that is small enough so that we still have an upper bound. And in that case, we take that as the new element and we ignore all the others, right? So this would be B1. And then we do the same thing for B1. So keep taking steps to the left, smaller and smaller and smaller and smaller, until you get something that is still an upper bound, something that still fits in between. And you call that B2, right? Actually, I mean, the way I set this up, B0 could be the same as B1, B2, and this goes on for a while until this is maybe B7, right? Because like I said, you don't change, you keep a different index, but you don't change the number until it fits. So maybe this is B11 and so on. So the point is, as this sequence goes on, it approaches E without being inside of E. I mean, it could be an element of E. What I'm saying is, it still has to be an upper bound. That's the only condition that we care about, right? So hopefully this recursion makes sense. And once we do this, there's nothing to prove about this recursion, but by an inductive argument, and we can fill this in. If the sketch above made sense by an inductive argument, each Bn is an upper bound because that's the way we pick it, right? Bn doesn't change if it's not an upper bound. And if it is an upper bound, then we always pick the one that is an upper bound, right? So all the Bn's are always upper bounds because that's how we are choosing them. But there's something more important about this, and that is that Bn is an upper bound by induction, but Bn minus 1 over 2 to the n is not, because if it were, that one would have been picked in the next step, right? So just think about this for a while. This isn't actually that complicated. The point is that knowing this, what can we say about this? So why does it matter that this is not an upper bound? So let me drag this down. I don't know why this gets so laggy sometimes. So then, for m bigger than the index, the current index we are at, if we take Bn, this number that is not an upper bound, this has to be smaller than Bm, because this is an upper bound, right? So if there's something that is not an upper bound, well, it has to be smaller than all the subsequent elements. And also something that should be obvious is that Bm is always at most Bn. This is a decreasing, not strictly decreasing, but it is a decreasing sequence because every element is obtained by either copying the previous one or subtracting something from the previous one. So these don't get larger. They might stay the same, but they usually get smaller, right? So Bm is at most Bn. That is definitely true. Okay. So now combining these two inequalities, combining these two last inequalities, what can we conclude? What is the distance between Bm and Bn given these indices? Well, they're both inside this interval, so it couldn't have exceeded 2 to the, let's say, actually, for any two of these, right? If we pick any index, any two indices bigger than n0, then the distance between these two has to be smaller, right? That follows from from the previous two inequalities. In other words, it's a Cauchy sequence. En is Cauchy. Oh, and I should say something. So B0 is a natural number, or sorry, an integer. I mean, we could just have picked a natural number. Let's say B0 is an integer. And if I subtract this from an integer, I get a rational number. And if I subtract that from a rational number, given that this is also a rational number, I get another rational number. So all of the Bn's are rational, because that's the way we picked, is a Cauchy sequence of rationals. And this is very important. These are only rational numbers. So now, what we do is use the construction of the real numbers, right? Okay, so let me see how we can write the next step. Okay, so something that is just a matter of pushing around the inequalities is, if I'm not mistaken, exercise. That it follows. This is just to keep the proof short. I'm not skipping anything. I'm not skipping anything important. But something that we conclude from here is that Bn minus 1 over 2 to the n is less than or equal to u. Or, actually, let me write this. Okay. Let me add this below. Maybe I should add a few more details. So actually, there's no exercise here. Just okay. So let u be the real determined by this sequence, right? Every Cauchy sequence of rationals defines some element, right? So basically, u, if you remember how we defined this, is the class of this Cauchy sequence of rationals. We put this in the class under, I think I called it C for Cauchy. So that is basically what U is, right? And here we're secretly using this weird property that every Cauchy sequence converges. So U is the limit of this Cauchy sequence. So this property is crucial for what we're trying to do. Okay, so based on these inequalities, the fact that this is a decreasing sequence and all of this, we can conclude that every time we subtract 1 over 2 to the n, this has to be at most u, right? It cannot be bigger than u. And also, it's a decreasing sequence, right? So they approach u from the right. So this happens as well for all n. Okay, so now the claim is that u is the supremum of E. Let me write that like that. U is the supremum of E. And notice that this is very intuitive. Just look at the sketch that we did here. We are approaching E from the right, making sure that we are always staying as an upper bound and only touching rationals, only mentioning rationals. So we take this and using the way that we built the reals as a complete space, using this property, what we're doing is we are claiming that this must have a limit. This must converge somehow. We don't need to talk about convergence or limits because that's just how the reals were built as representatives of these Cauchy sequences. So let U be that representative, and U must be whatever these BNs are approaching. But if you look here from the sketch, doesn't it seem very intuitive that whatever they're approaching is actually the supremum? It's something that is touching, barely touching E, the least upper bound, right? So actually, this isn't an exercise. That's not necessary. I added the missing details. But let's say that this claim is an exercise. It's a good way to test your understanding of this proof. And there is nothing that you need to prove this other than what is already written on the screen, right? It's a very short proof. So claim, if you want, we can do one of the two parts. We have to show that U is an upper bound, and then we have to show that it is the least upper bound. So there's two steps that are missing. Should we do one of them? First, let us show that U is an upper bound. So any element of E is at most U. Now U could be an element of E. We cannot discard that possibility. So by contradiction, let's prove this part. And then the second part can be left for an exercise. Contradiction. How do you spell contradiction? Contradiction. Suppose Suppose that it is not an upper bound. If it's not an upper bound, then there must be some element A that is bigger, right? If it's not an upper bound, well, it's not above everything, so there's something above it. And now what we do is we use the inequalities and the fact that this is approaching. So by Archimedean property, let me just say, so pick a small and a large enough power of 2 such that it is bigger than this, A minus U. And hopefully this makes sense. Let me think about this pick. Yeah, I think this one works. Because then we can just say that 1 over 2 to the n is smaller than A minus U, right? We're just flipping that around. And then adding this to the previous inequality, what we get is that Bn minus 1 over 2 to the n plus 1 over 2 to the n is less than U plus A minus U, which is A, and this is just Bn. And we get a contradiction because Bn is supposed to be, all the Bn's are an upper bound of of E. But we just found an element that's bigger, right? So this is impossible. which is impossible because Bn was supposed to be an upper bound. Every Bn was chosen to be an upper bound, which is impossible. Second, we show it is the least upper bound, and I think we can just leave this part as an exercise. It doesn't use any argument that's too different from the one we have here. All the inequalities come into play, and that's how we conclude that EU has to be the supremum, right? So this is what it means for a set to be complete. There are no holes because every time you have a set and something glued to it, that must still be part of the real numbers. Now maybe you can see why this is connected to the closure operation. So maybe I can add this. This is part of the problem set. I think the part that you don't have to turn in. So here's another simple exercise that connects these two concepts. If U is the supremum of E, regardless of what E is, then U has to be in the closure of E. You can prove this very easily from the definition of supremum, the fact that it is the least upper bound, right? You can invoke a sort of contradiction argument. It's a good exercise to practice writing about this. Another exercise that's relevant to the problem set is showing that completeness doesn't just apply for the upper bounds, right? Also, every lower bounded set, non-empty set of reals, has an a greatest lower bound, an infimum. And you don't have to you could redo this entire proof, just adding instead of subtracting and making an increasing sequence instead of a decreasing one. But you can actually use this theorem to prove that other one, and that is exercise either 1 or 2 in the problem set, in the current problem set. So hopefully that makes sense for you. Okay, so the next concept that we're going to talk about is compactness. We already know what it means for R to be complete, but we don't understand it very well yet because we have to consider other approaches. I've talked about the algebraic approach, which is Cauchy sequences. That one is immediate, right? Every Cauchy sequence has a limit because that's what the real numbers are. The real numbers are the limits of Cauchy sequences in a way. We just talked about the order. Supremum is a quality of order, right? There's no need to talk about algebra. When we define a supremum, it is something purely in terms of less than or equal to for the real numbers, which is interesting. And we did use that, right? We found a decreasing sequence and did a whole bunch of stuff, but we have to connect this to algebra. And that's why we invoke the Cauchy sequences of rationals. So the next step in our chapter, which I will look at how much time we have in total, maybe it's already too much. The next step would be to consider compactness and try to rewrite what it means for R to be complete in terms of compactness. And for to do that, we're going to develop some interesting proving techniques that hopefully you find interesting. And this is very powerful stuff that's connected to a lot of things, not just in real analysis, but in other fields of mathematics. So it might not seem that way right now. It might seem like this is just a very specific technical theorem, but this is actually quite deep and, like I said, connected to many other things. And if you're curious, feel free to ask me what you could do with compactness. Because as we will see in the next section of this chapter, compactness is a way to turn something in the theory that is infinite into something finite. And that is not a trivial idea, and it is important in many contexts. Let me stop the recording for now.